In our last lecture, we have discussed elementary transformations. Means in case of matrix, if you want to transform any two rows or any two columns, then there are three elementary transformations. Today we are going to discuss the concept inverse of a matrix. So we will discuss this in detail today. So let us see inverse of matrix. Now let us see the definition. If A is a square matrix, first of all remember inverse of a matrix exists if A is a square matrix. So here if A is a square matrix of order M, here it is given in general order M, and there exists another matrix B of the same order. See the proper definition. A is a square matrix of order M and there exists another matrix B of the same order such that A into B is equal to B into A is equal to I. I denotes identity matrix or unit matrix of order M. Then matrix B is called the inverse of A. Means what? See here, the product between A and B or B and A, it gives identity matrix. Then B is called as inverse of A. Remember this definition. AB is equal to BA is equal to I. Just like in case of number, if the number is given 2, then its inverse, multiplicative inverse is 1 by 2. So 2 into 1 by 2, we get 1. Like that, here A into B is equal to B into A is equal to, if you get identity matrix, then B is called the inverse of A. Now inverse of A is denoted by A inverse like this. A raised to minus 1 means A inverse. And hence, how will you write that equation? Here, A into A inverse is equal to A inverse into A is equal to I. Here, product is commutative here. A into A inverse is also I. I means identity matrix or unit matrix. Or A inverse into A is also identity matrix. Okay. Now see, when the inverse exists, means first of all matrix must be square matrix, but inverse of square matrix exists if matrix is non-singular. We know the type of matrix, non-singular. When the matrix is said to be non-singular, means square matrix is said to be non-singular when determinant of A is not equal to 0. In the types of matrix, we have discussed this type, that is non-singular matrix. So what are the conditions for the existence of inverse of matrix? First of all, matrix must be a square matrix and that square matrix must be non-singular. So remember this carefully. So inverse of A is denoted by A inverse and inverse of square matrix exists if matrix is non-singular. So we have discussed the definition and the condition or existence of the inverse of matrix. Okay. Now let us discuss another point. Now see, there is a theorem or theoretical proof is given that for uniqueness of the inverse of a matrix. Now for a square matrix, if it is non-singular, then inverse exists and it is a unique inverse. Inverse must be unique. So inverse always unique. So that uniqueness we will prove in this theorem. So it can be proved that if A is a square matrix where determinant of A is not equal to 0, then inverse is denoted as A inverse and it is unique. So let us see the theorem which is given in your textbook. Directly just we will discuss it theoretically. So prove that if A is a square matrix and its inverse exists, then the inverse is unique. Now we will prove this uniqueness of inverse. So inverse exists. but whether it is unique or not, that we will discuss in this proof. So let us see the proof. Suppose let A be a square matrix of order m and let its inverse exist. So existence of inverse is there because A is given as non-singular matrix, so inverse exists. So suppose let it possible B and C be two inverses of A. Suppose if we consider that there are two inverses of A, we have to prove that inverse is unique, but here we consider contradictory that B and C are inverses of A. Then what happens by definition of the inverse? How will you write the equation? A into B is equal to B into A. You will get I because B is inverse of A. So A into B or B into A, it gives I. Similarly, A into C is equal to C into A is also I, because we know that as C is the inverse of A, so A into C it is also equal to I. Similarly, C into A is also I. So this is by our consideration. Now to prove the uniqueness, we will consider matrix B just. Now B can be written as B into I. It is possible because if you multiply any identity matrix to B, then it gives B. Okay, so B into I is always B. So we consider like this. Now B, keep B as it is. Just we will solve this equation theoretically. B as it is. Now in place of I, you can write A into C because A into C is I. So proper use of these two equations we will consider like this. So B, it gives B into bracket A into C. Now by associative property, we can write it as, we can take bracket here. So B into A into C. So give the bracket to B into A. Now as per this equation, B into A is also I. So what you will get? I into C. Now we start with B, that is B is equal to B into I, and we get here I into C by this step. So what happens? I into C is again C because you multiply by identity. So that gives B is equal to C. So hence, as it is B is equal to C, that is, we can say that the inverse of matrix is unique. So we have considered there are two inverses of A, but we have proved that B is nothing but it is equal to C. So B and C are same. So now onwards, you always remember, if the inverse of a square matrix exists, then it is a unique. Okay, so this is a uniqueness of the inverse of a matrix. See this proof, theoretical. So what we have discussed, what is the meaning of inverse, that is A into A inverse or A inverse into A is equal to identity matrix. Then A inverse is called as inverse of a matrix, inverse of a square matrix. Then existence of inverse, inverse exists if the square matrix is non-singular and that inverse is unique. Okay, now how will you find out the inverse of a matrix, that we will discuss. So let us see. Now inverse of a matrix in bracket, if it exists, can be obtained by any of the two methods. So there are two methods given. First method is elementary transformations and second one is adjoint method. So there are two methods to get the inverse of any square matrix. Now today we will discuss about elementary transformations. Adjoint method we will discuss in our next lecture, but today we will discuss elementary transformations. Okay, so let us see elementary transformations, or how will you apply the elementary transformations to get the inverse of given square matrix. So now see here, if square matrix A is given to you which is invertible, invertible means inverse exists. So that is called as invertible matrix. So A is invertible matrix means existence of inverse. So it is a square matrix given to you. Then we can write A into A inverse is equal to A inverse into A is equal to I. That is identity matrix. This is by definition of inverse. Now take A into A inverse is equal to I. If you take A into A inverse is equal to I, this equation, okay, say this is equation number 1. Now what is the method here? By elementary transformations. If you take this equation, because there are two equations here, A into A inverse is equal to I, also A inverse into A is equal to I, but if you take A into A inverse is equal to I, then to get the inverse of matrix A, what is the procedure? See here, convert this equation as, see, I into A inverse is equal to B. So original equation is A into A inverse is equal to I. Now by suitable elementary transformations, we have to convert this equation in the form of I into A inverse is equal to B. That is, and from that we get A inverse is equal to B. Now what is the change in this equation? See, A gets converted into identity matrix. See, A gets converted into identity matrix. A inverse remains as it is and is equal to, on the right hand side it is I, and it gets converted into another new matrix B, and hence as I into A inverse, that is A inverse, and hence A inverse we get it as B. So after solving this equation we get this equation. Now in this case what happens? So in equation 1, prefactor is converted into I. See, A is what? A is prefactor. A is converted into I, and on the right hand side I is converted into a new matrix B. So prefactor is converted. Remember, I have given in bold letter, prefactor is converted. So that new matrix B is called as inverse of A. Now whenever you want to convert the prefactor, see, again and again, whenever you want to convert prefactor of the equation, then in this case we have to use row transformations. So in case of elementary transformations, we have to use suitable row transformation if you want to convert prefactor, because we start with A into A inverse is equal to I. By suitable row transformations, this equation will get converted into A inverse is equal to B. So always remember, when you want to convert prefactor, then use the row transformations, because here compulsory we have to convert the prefactor, because prefactor gets converted into I, and this I converts into B. So that's why we get A inverse is equal to B. Don't convert this A inverse, okay? A inverse remains as it is because LHS contains A inverse. So A inverse is equal to B. Okay. In our last lecture we have discussed that whenever you want to change the prefactor, then use row transformation. Just we apply here to get the inverse. Now consider another case. Again same, if square matrix A is given to you which is invertible, means inverse exists, then we know this equation. And now if you start with this equation to get the inverse, if you write A inverse into A is equal to I, if you take this equation, say this is equation 1, then how will you get the A inverse here? We have to convert this equation as, see, A inverse keep as it is. By suitable transformations, by suitable elementary transformation, we have to convert this A into I and this I to B. So use the suitable transformation so that you will get this equation, and hence we get the inverse, that is A inverse is equal to B, because A inverse into I is A inverse. So A inverse is equal to B. Okay. Now in this case what happens? See, if you take this equation, then we have to convert the post factor. See, this is called as post factor. Okay, so post factor is converted into I. See, post factor is converted into and I is converted into a new matrix B, and that new matrix is called as inverse of A. So hence we get A inverse. A inverse is equal to B. And if you want to convert the post factor of the equation, here we need to convert the post factor. So we have to use column transformations. Okay, so when we have to use the row transformations and column transformations, if you want to use, see here, take a note that if you use this equation, that is A into A inverse is equal to I, then use row transformations. Okay, in short, you remember this. If you start A into A inverse is equal to I, then row transformations, because we have to convert this A, that is called as prefactor. So prefactor gets converted into I and I converted into B. So use suitable row transformations. And if you take this equation, A inverse into A is equal to I, then use the column transformations. Okay, so remember this. There are two elementary transformation. One is row transformation and other is column transformations. Now see actual steps. How will you convert the equation? Now how to convert given matrix A, because here we have to convert matrix A. Here also we have to convert the matrix A to matrix I. I have taken the example of 3 by 3 matrix. See, this is 3 by 3 given matrix, and we have to convert this matrix by suitable transformations. It gets converted into I. I means identity matrix. So what are the proper steps? So see here, how will you convert it? Now, if you want to use row transformation, means if you take this equation and if you want to apply the transformations, then we have to use row transformations. Now, what is our aim? We have to convert this A to I. So, how will you convert this? So, what are the proper steps here? See here. Now what happens? See, this matrix is converted into identity matrix. So first of all, use the suitable row transformations so that reduce A11 means this element to 1, because if you want to convert this matrix to this, then convert A11 as 1. Means first step that we have to use is what? To convert A11 or to reduce A11 to 1. Then next step will be you have to convert A21 and A31. See this, A21 and A31 to 0. See here, you will get 0 here, 0 here. So first step we have to use, we have to convert this element to 1, then these two elements to 0. Then third step will be for to convert A22 to 1. Convert A22 element to 1. See here. Then fourth step will be reduce A12 and A32 to 0. This A32 and A12 or A12 or and A32 to 0 means make this to 0. Then reduce A33 to 1. Reduce this A33 to 1, and last one reduce A13 and A23 to 0. So these are the proper steps. If you want to convert this matrix to this matrix, then you have to convert A11 to 1, then these two to 0, then A2 to 1 and these two as a 0, then this A33 to 1 and other these two as 0. So follow these steps properly for row transformation. Okay, don't change all these steps. Means if you try to convert first this 0, then this 1 or this one randomly, then you will not get a proper inverse of the matrix. Okay, so always use all these steps to get the inverse of matrix, or if you want to try, if you want to convert this matrix to this matrix. Okay, so this is for row transformations. Now in case of column transformations, what are the steps that we have to follow to convert again this matrix to this matrix? Because here also we have to convert A into identity matrix. So first of all, in this case also we have to reduce A11 to 1. Again here A11 to 1. But second step will be reduce A12 and A13 to 0. Okay, so after getting 1 here, you have to convert these two as 0. Okay, these two as 0. In case of row transformation, we have to convert these two as 0. See here, compare both the steps, both the cases. Okay. Now third is reduce A22 to 1. A22 to 1 here. Reduce A22 to 1. Then fourth step is we have to convert A21 and A23 here. A21 and A23 to 0. And then reduce A33 to 1 and then reduce A31 and A32 to 0. See. So in case of column transformations, we have to convert this element to 1, then these two as 0, then convert this element to 1 and other two as 0 here, and then last convert this element as 1 and these two elements as 0. So see the comparatively. Okay, while performing row transformation we have to follow all these steps, and while performing column transformations we have to follow these steps, and same transformations we have to apply on the RHS of any one of these equation. If you want to perform row transformation, then use this equation, and if you want to perform column transformation, then use this equation. In both the cases we have to convert A to identity matrix. So if you want to convert this matrix A to the identity matrix, same transformations if you apply to I, then you will get a new matrix that is called as B, and it is nothing but the inverse of matrix. So perform these row transformations or column transformations. Okay, so this is all about the inverse of a matrix, and in that case today we have discussed elementary transformations, in which row transformations and column transformations. So today we have studied theoretical part of this inverse of matrix. In our next lecture actual we will find out the inverse of given square matrix. So remember all these concepts, theoretical concepts related to find out the inverse of matrix. Okay, thank you.